there's a lot of vanadium in the ground. This data is from the U.S. Geological Survey, looking at reserves of about 14 million tons of vanadium in the Earth's crust. If you do the math based on current consumption, there's enough vanadium for us and our kids and our grandkids and a few generations after that. The problem, though, is that a lot of this vanadium is not in economically viable deposits. So looking at the over-the-top number really doesn't describe the picture very well. But the point is there's a lot of vanadium out there. Finding the right deposit to develop is really the key. Talking about vanadium consumption, if we look at consumption today, consumption this year of vanadium is probably going to be around 89,000 tons, close to 90,000 tons of pure vanadium per year. This data from last year, and you can see where the vanadium is being consumed in terms of countries. And obviously the 800-pound gorillas are Chinese friends here. But obviously North America, Europe, and other parts of the world are significant consumers of vanadium as well. Looking at applications, today about 90% of the vanadium in the world is consumed in the steel industry. And there's really two classes of steel that consume vanadium. Carbon steels, by adding a very small amount of vanadium, half a kilo of vanadium per ton of steel, in many cases we can double the yield strength of that steel and in essence double the utility of that material when we're talking about load-bearing applications. So carbon steels, we put a little vanadium in them and we have a class of steels called high-strength, low-alloy steels. That's the major application for vanadium today. So carbon steels, we put a little vanadium in them and we have a class of steels called high-strength, low-alloy steels. That's the major application for vanadium today. Also in the steel industry, there's a significant amount of vanadium consumed in high-alloy steels. These are, for example, tool steels or high-speed steels that in many cases will have vanadium content from 1 up to 10 or 15%. Outside of the steel industry, the titanium alloy industry uses vanadium. About 4% of consumption today is going into the titanium alloy industry. These are alloys that are used primarily in aerospace and defense applications. The workhorse alloy in the aerospace field is titanium 6-4, which contains 6% aluminum and 4% vanadium. Right now, the titanium industry is moving into an upswing in the cycle. Last week, we had a conference in Chicago, the International Titanium Association, and the projections are that titanium melting is going to go up by about 50% over the next 5 years. And actually, the amount of vanadium that will be consumed will increase even more than that, because right now, there's a lot of scrap being melted in the titanium industry. They've maximized the utilization of scrap. When they melt scrap, the vanadium comes back into the melt. But the amount of scrap that's available is being depleted now, and as they go forward, they'll be melting more virgin titanium and vanadium master alloys to produce this. So we could envision vanadium consumption in titanium industry doubling in the next 5 years. So that certainly can have an impact on the market. Chemical applications, you've got all sorts of very unique chemicals, from sulfuric acid catalyst to maleic anhydride catalyst to pigments and fluxing agents for ceramics, coatings for glass, all sorts of applications for vanadium in the chemical sector, pollution control catalysts that contribute 3 or 4% to the consumption. So today, the steel industry is the big driver. The 1% there that for some reason my slide's not showing on the legend here is energy storage. So today, there's really not a huge amount of vanadium going into energy storage applications, for example, VRBs, but that certainly looks like it's going to change in the not too distant future. This picture is just showing the growth in world vanadium consumption, and you see from 2001 to 2012, consumption's essentially doubled. We see the dip there in 2008, 2009, as a result of the global financial crisis, but it's interesting to see you see the slope of this line after 2009, and you can see the rate of consumption is growing at a very strong level globally. There are two major drivers to the consumption of vanadium based on the consumption patterns today, and they're both related to the steel industry. One is just the total number of tons of steel produced globally. As that number changes, the demand for vanadium is going to change. But the second, maybe more opaque variable is the specific vanadium consumption rate. How many kilos of vanadium are consumed for every ton of steel that's produced? And today, roughly 10 or 11% of the steel produced in the world contains vanadium, but that ratio is going up dramatically year by year. So the number of kilos of vanadium consumed per ton of steel produced globally is moving up, and there's very good reasons for that. And we talked about adding a small amount of vanadium, half a kilo of vanadium to a ton of steel to double the yield strength. So if you're in China and you're in the middle of this massive project to build infrastructure to allow for the development of industry and creation of jobs and improvement of the life for the people, there's a massive demand for steel that's growing every day, and that has some negative consequences. The consumption of raw materials, consumption of energy, deployment of capital in steelmaking capacity. There's a lot of negative impacts of this surging steel demand in China and elsewhere. And all of those negative impacts can be mitigated to a great extent by substituting high-strength, low-alloy steels for plain carbon steels. So if I take a carbon steel and I add a half a kilo of vanadium to that steel, and it's really just that simple, and in many cases double the yield strength, I've increased the cost of that steel by 2 or 3%, but because the yield strength is twice as high, I can go out as a steel maker and sell that steel for 20 or 25 or 30% premium. I win. The guy's buying the steel. If I'm building a building here and I need to support a certain load, and I've got my choice to use low-strength steel at one price or high-strength steel that's twice as strong with a 20 or 25% price premium, I'm going to use a high-strength steel. I'm going to use 30 or 40% less steel, so the total cost of the steel going into my structure is going to be lower. The amount of raw materials consumed to build a given amount of infrastructure is minimized, the amount of energy consumed, amount of pollution generated, the amount of capital deployed to build out a given amount of infrastructure. There's benefits for everybody in that value chain, and for that reason, we see this ongoing substitution of carbon steels for high-strength, low-alloy steels, whether they utilize vanadium or niobium or titanium or some combination thereof. It's a very efficient way to use steel to build your infrastructure. So those two parameters, steel production and specific consumption rates, changes in those are the major drivers historically in changes in vanadium demand. Looking ahead, the titanium industry, again, I call this a minor driver. We say demand might double, but you know the quantity of vanadium that's consumed, about 4% of the total today, could double. That certainly have an impact. I guess maybe it's not a minor driver, it's maybe a midterm driver. Looking down the field, what's coming at us? I'm sure everybody's heard about the vanadium batteries here and the redox battery, and this certainly has the potential for changing the demand of vanadium significantly. When you look ahead and try and forecast what's going to happen, coming from my background as a vanadium producer, you always want to try and you sit down, you build your business plan, you build your budget based on a conservative environment so that you can survive no matter what happens and take advantage of some of the upside. So from my perspective, looking forward, we always say, okay, what's going to happen in terms of demand? And you say, okay, vanadium batteries, what's it going to mean? Well, I don't know. I mean, it feels like it's going to be quite important quite quickly, but it's very difficult to forecast. So when I look at my forecasts, I omit really much of anything going into this application. So if we look at this data and look at the implications, and then anything that happens in terms of demand for energy storage is going to just go right on top of the picture I'm going to paint here today. Specific vanadium consumption rate varies country by country. Here's the data that shows you that in North America we consume on average just about 0.09 kilos of vanadium per ton of steel. The world average is about 0.056 kilos of V per ton of steel. And if you remember, I said a typical HSLA steel has about a half a kilo per ton of steel. So you see the global average is only about 10% of the actual consumption of vanadium high-strength steel. So again, about 10 or 11% of the steel today contains vanadium, but there's plenty of space for that to move up. And interesting, you see the areas of the world where steel production is growing the fastest have the lowest specific consumption rate. This is typical as their industries mature and the knowledge and science improves in these areas. You see them moving more quickly to adapt higher strength steels and consume more vanadium. So what's happening is across the board, all these specific consumption rates are going up, but these ones are moving up much quicker, and that really has some strong implications for the demand of vanadium. Looking at global steel production, historically, you can see that just around 2000, we've seen a significant change in the environment in the steel industry with growth rates moving up. I'm not sure if you look at this data and compare this to global GDP, you're going to see that over the last 10 years, steel production has grown by about 1.8% per year above global GDP rates. And that's really been driven by China. Now the question going forward is what happens from here? Do you continue to see the same pattern in other parts of the developing world, India, Southeast Asia, the Middle East? And will steel production rates continue to grow at such high rates? It's difficult to say. There's a lot of projections out there. In general, I think if you look at 3 to 3.5% growth rate, it's very modest compared to what we've seen recently, and that's probably where most of the pundits are falling out right now. So if you have steel growth rate of 3% a year, that's going to have some impact on the consumption of vanadium. Here's the data looking at specific consumption rates, and again, you see here the North American numbers on top, and you see India down here. The interesting line in this picture is these other countries where consumption has moved up rapidly, and then you see what's come here in China the last couple of years. Again, if you do the math, tons of steel produced in any one country times the specific consumption rate, that's going to tell you how much vanadium they're consuming. And because there's so much steel produced in China, what you see is the changes in the situation in China having a big impact. All right, we already talked about this data. This is what's going on in China right now. This is the consumption of vanadium only in one application in China. This is reinforcing bar used for concrete construction. Back in 2004, China adapted a new standard for reinforcing bar. This was after the massive Sichuan earthquake, when they had a real problem with buildings failing catastrophically. If you have an earthquake, the first thing you have after an earthquake is a fire, and you have a lot of heat. Steel, if it's not strong enough, loses its ability to support the load at high temperatures, and the building's pancaked. So what they did is adapt a new standard for rebar, the grade 3 standard, which requires higher yield strength, 350 megapascal yield strength, and a elongation specification, the ultimate to yield strength ratio of minimum of 1.25. And what that means is the steel is somewhat ductile, so when the ground starts shaking, the steel can give a little bit without catastrophically failing. And this steel, grade 3 rebar, is very simply made. We make normal grade 2 rebar, carbon manganese steel. We put in, depending on the size of the bar we're going to make, between 0.3 and 0.5% vanadium, so 0.3 to 0.5 kilos of V per ton of steel into that steel, and we meet the specifications. So in 2004, really overnight, this new market developed, and we saw this surge in demand coming from China. And what happened is the price reacted. The market got overrun. China's always been an exporter of vanadium, and suddenly they became a net importer. And if you go back and look at the price history, you'll see the 2004 price spike where prices shot up to a ridiculous level. And when vanadium got to $130 a kilo, it just becomes economically unviable for people to use. And so what you saw is when prices reached ridiculous levels, we saw some substitution here. And what this is people basically using substitutes for vanadium to make that grade 3 rebar, specifically in this case moving to niobium plus titanium rather than vanadium. Now, you can do that, but there's implications. And if you look at it from a metallurgical standpoint, niobium, titanium, and vanadium, they all strengthen steel, but they do it through very different physical metallurgical processes. So you can get to the same yield strength, but there's implications in terms of processing, in terms of how the steel is going to perform in the field. And there's always a best way to make a certain type of steel. And sometimes it's vanadium, sometimes it's niobium, sometimes it's titanium. There's always metallurgically a best way. But when the economic factors get out of whack to a big enough extent, what you see is people forcing that square peg into the round hole. So in this period, a lot of these rebar producers moved to niobium plus titanium. It's difficult to do because you have to have a very controlled rolling practice. You have to reheat the billets to a very high temperature to get the niobium in solution. You have to have a very powerful mill to get the cross-section reduction about 50% in each pass. You've got to cool the steel down below the transformation temperature between each pass. So it's difficult to do. And in terms of the quality of the product, if you don't have the very precise cooling rate with the niobium microalloying system, you get different microstructures at different parts of the bar across the diameter. You get warping, you get embrittlement, you get breaking out in the field. So there's negative implications. And so what happened is people moved to niobium, the price came back down, and then once the price came down to a reasonable level, they turned right back and started using a vanadium again because it's just the best way to get there. And so what you've seen now is as this grade 3 standard's been adapted in China, is a massive explosion in consumption. So we're talking about 25,000 tons of vanadium, which is, somebody smarter than me can do the math, but that's 40% of global consumption in a new application that didn't even exist 10 years ago. And there's plenty of room for this phenomenon to continue. If you look at what's going on right now, the percent of rebar that's being produced in China that's meeting this grade 3 standard is still only about 60% of the total. So this 25,000 tons can easily turn into 40,000 tons over the next couple of years. And we're only talking about rebar here. We're not talking about structural steel, H-beams, I-beams, all sorts of applications where adding vanadium to the steel impacts the strength and makes it much more valuable for the producers and the consumers.